In section 5.1, we will review and study section properties. Okay, the cross-section properties for a simple shape, for a simple shaped cross-section, include area, moment of inertia, etc. So normally we use A to denote area, and Ix, Iy to denote moments of inertia with respect to x and y-axis, respectively. And we use Ixy to denote product of inertia with respect to x and y-axis. And polar moment of inertia equals Ix plus Iy. And Ibb denotes moment of inertia with respect to axis bb. For a rectangle, so as shown here, the A, very simple, the A equals BH. And the Ix, since we're x, it's in this direction, just going through the centroid. Y here going through the centroid. So y is the x. So the Ix, moment of inertia with respect to x, equals bh cube over 12. And Iy equals hb cube over 12. And the Ixy equals 0. And Ip equals bh over 12 times h squared plus b squared. Okay, those are the basic properties of a simple shaped cross-section, a rectangle. Okay, we gave the equations to calculate these section properties for simple cross-sections, simple shapes. You can see that for a square, for a circle, right, this A equals just pi r square or pi d square over 4. Ix equals Iy equals pi d to the fourth over 64. And Ip equals Ix plus Iy, right? This will be 2 times Ix. This will be pi d to the fourth over 32. What is this? This is a J, right? This is a J in last chapter when we talk about torsional elements, torsional shafts. Okay, so this is just the polar moment of inertia. Well, the moment of inertia for area is actually a geometrical property of an area which reflects how its points are distributed with regard to an arbitrary x. Right, so what does this mean physically? So physically, it may not mean something, but as I provided a link here, so you can click this link to watch this short video. It perfectly demonstrated what does the moment of inertia for mass mean. Okay, meaning that how hard a shape with the same mass can be disturbed. Okay, so how can you play a specific weight easily when this mass is distributed in different manners through a object. Okay, so how about the moment of inertia for area? This, in terms of beam, so this will mean that how hard this beam section will be bended. Okay, as shown here in this simple rectangular shaped beam cross section, the Ix equals bh cube over 12, and Iy equals hb cube over 12. Okay, and this shape is not that obvious. The differences will not be that obvious. How about let's compare these two when b equals 1 and h equals 10. Okay, when this shape become something like this. Okay, you have b here, h here, b equals 1, h equals 10. Then what is Ix? X direction and y direction. What is Ix? B h cube over 12. It would be 1,000 over 12. That will be larger than 80. Right? Then how about Iy? Iy will be h 10 times 1 over 12. That will be smaller than 1. Okay. Okay, this time the Ix is much larger than Iy. So what does this mean? Look at this area. Okay, if you just use it as a cross section of a beam with this cross section, if you just load it in this way. Consider that this is a deep beam with a cross section like this. Okay, if you support it here, and add a load P here, do you think this shape can be easily bended? Right, consider a ruler. Okay, this is just a shape of a ruler. Okay, consider this ruler. If you just load your ruler in such a way, can you bend it? A plastic ruler, can you bend it? Very hard. Okay, then how about put it down? If you put it down, okay, the same ruler, you put it down, and you will get some kind of a cross section like this. Right? Then you support it here, then add a load P. Is that easy to bend it? This time it will be very easy, right? If you have a plastic ruler, try to do this experiment. Okay, put it in number 1 and number 2. These are two scenarios to compare the hardness to bend this ruler. Okay, so this experiment will tell you what does this mean. What does I mean? Okay, this Ix is much larger than Iy, meaning that if you set the beam in the manner 1, it can hardly be bended. But if you set it in manner 2, it will be easily bended, although you are using the same thing as the beam member. Okay, so hope this video and this experiment can help you understand what this moment of inertia mean. The moment of inertia about axis that pass through its centroid is minimum in that direction. It is about this axis passes through its centroid is minimum. If we're calculating the moment of inertia about any other axis parallel to this axis passing through its centroid, you will get a larger value. Okay, the moment of inertia about any axis parallel to its centroid axis is given by this equation. Okay, it equals this IC, the moment of inertia about the centroidal axis, plus A times d squared, and the A is the area of the shape, and the d is the distance between these two axes. Okay. Then we have another thing that is critical in this analysis, that is the centroid, the location of the centroid. Okay, this is the point that defines the geometric center for an area. Okay, if you have a random shaped area, then the centroid can be defined from such equations. It's just mathematically meaningful equations, but mechanically, especially in this entry-level mechanics class, this means nothing. Okay, so the centroid, if I give you a rectangle or a circle, it's easy to find the center. Right? Then how about a composite area, composite section? As shown here, if you have a T-shaped beam or an I-shaped beam, okay, then how to find the centroid of these composite areas? Okay, here are the equations, the methods to tell you how to find out the centroid of such sections and how to calculate the moment of inertia of it. Okay, the centroid of section, the location x bar and y bar can be found by these two equations, and normally we only deal with symmetric cross sections, meaning that you only need to find y bar, since x bar will always be in the center of this shape, because it's always located on the axis, right? Because it's centroid. It's a symmetric. Okay, so this x bar is not needed to be determined. We only need to determine y bar. So that is the distance from the top or the bottom to the centroid of this shape. Okay, then the look at this equation. This equation would be just y bar equals sum yi ai over sum of ai. Right. This yi is the distance of a centroid of each subsection from the original, or from the top or the bottom of the section. This is based on how you select the origin. Okay. And moment of inertia, we just need to cut it into sub-areas, subsections. For example, in this I-shaped beam, like here you can just cut it here, so you get area 1, area 2, and area 3. You need to cut these subsections, so when you calculate, when you're finding the centroid of the section, you also do the same cut when you calculate the moment of inertia. Right? Get these 3 sub areas, and then for each of them you calculate is IC plus D squared times A based on this equation. Right? Then you sum them together. Right? You sum them together, and you will get the overall moment of inertia. Okay, these are the theories. Then we will give several examples to show you, to demonstrate how to consider different kind of cross sections, composite areas, to find out the location of centroid and determine the moment of inertia.